So today's topic is filter design, right? So let me grab my pointing stick. So today we talk about IIR. So do we still remember what is IIR? What is FIR? FIR, I found this a singing group. 有个歌唱团体好像叫 FIR. I just recently learned that. But in here, FIR stands for finite impulse response. IIR is impulse response. IIR is infinite, finite versus infinite. 有限的、无限的. Infinite impulse response filter, the impulse response is going to last forever. Yeah. And today's topic will be under this name, the Butterworth. That's the name of a IIR filter. And so here is the outline. So today we first talk about the analog prototype. So as we mentioned in an overview last week, in IIR design, we start by using existing knowledge in analog. Okay, historically we borrow an analog prototype, 一个雏形啊 prototypical analog filter. We'll study that first, and then after that we will introduce one method to change an analog system, to map an analog system. A transfer function, h of s, transfer function. We want to make a transformation so that becomes a digital transfer function as a function of z. So from S domain to Z domain, bilinear transformation is a mapping from the Laplace S domain to the Z domain. Okay, so that's a transformation we're going to be using. It's called bilinear transformation, and then near the end of this lecture, I will provide some extended reading materials. So that's today's outline. Okay, so now let's start. So this is the analog prototype. Okay, analog prototype, and you can find the complete coverage in the appendix B1 of the textbook, Oppenheim Schaefer, ONS, that's the textbook. Okay, so let's start slowly. So here you see we have a transfer function, a function of S, the Laplace S variable, S, which can be written as also it has a fractional expression on top. There's a constant that goes there. Omega C, as you will learn, omega C. C stands for cutoff or corner. Corner, should I say corner frequency? So here we have omega C, which stands for a corner frequency, and its unit might be in the continuous time scenario, the unit of the frequency. Angular frequency, we will 叫频率. Angular frequency is radian per second. So that's a unit for this constant, which stands for, which denotes a corner frequency. So that's on top. At the bottom, we have a factorization, so which goes as this product, 乘积, product. The product goes from 1 to big N, and big N being the order of the filter. Okay, so the order filter. So at the bottom denominator part, we have a polynomial of S of order N. Okay, it's going to be a polynomial, right? Just so when we factorize a polynomial into this form, so we know S minus something, that thing is one root, right? S minus something, so each of that thing is a root to the polynomial. 多项式的一个根. So far so good. So we have this expression of a product. Oh shoot! This frequently goes off. I may want to change the setting. It's going, and I'll hit my screen from time to time. Okay. So that's an expression. Maybe we can copy it. We'll use it later. Copy this expression, h of s. We're going to be using it later. Okay, h of s equals to, there's a constant omega c to the nth power. Not that important. And product k from 1 to big N. And then S minus each of the root can be written as this still omega C times each of the something. Okay? So each root has omega C times each of the something. E to the, there's a constant term, e to the j, no, e to the j pi over 2 minus, oh, did I write minus? Should be plus. I'm sorry. Yeah, this should be plus. Yeah. Actually, it should be plus. 2. Oh, no, that's correct. It's a constant. Yeah. Yeah. Things are getting tricky. Okay, 2n divided by, yeah. So we'll make a drawing. Okay, so these are roots. It's important to know where the roots are. Okay, so we'll do that later. But now let me finish copying this entire expression. Now it's k pi divided by n. Okay, yeah. All right, so pretty big expression right here. I'm closing this with a bracket. Okay, so that's h of s. So which is an analog system, a transfer function of an analog system. Okay. So later we are going to show that surprisingly, okay, by nicely placing all the roots, actually on the same circle, if you will. Yeah, all the roots are going to be on the same circle. Have you noticed? Because each root has a radius of omega c, which is a real number. The radius of omega c, which is a real number right here, right? Times each of something that's on the circle, on the same circle. We'll make a drawing, okay? So, but with this h of s, it turns out that we have a rather surprising outcome, that the frequency response. So I'm going to continue by giving you an interesting fact. Okay, if you look at this transfer function, it's an nth order polynomial down right here. But when we consider the magnitude response, when we consider the magnitude response, that is the transfer function evaluated on the imaginary axis. H of s, when we plug in s equals to j omega, that gives us a frequency response, right? It gives us a frequency response. So if we consider the magnitude response in particular, and let's add a square, we're going to show that it turned out that this magnitude response has a very simple form. And that's an important message I want to deliver, okay? Turns out that this exact transfer function has a very nice, simple-looking magnitude response. So let me write it. The magnitude response is just 1 over something. 1 over a thing that has very easy expression. Omega divided by omega c to the power of 2n. It's wonderful. Yeah. Very nice result. Okay. Yeah. So we do two things, okay? First, let's try to make a plot of this result. And then we check why this is the case, okay? Two steps. First step, let's make a sketch, okay? So let's try to, I invite you to try to make a sketch of this as a function of omega right here, right? So it is a function of omega, and we see that as omega increases, this bottom part, the denominator also increases. Therefore, the magnitude is going to keep decreasing. Right? So first thing we notice, the larger omega is, the smaller its magnitude response is. So in general, we have a monotonically decreasing frequency response. The magnitude response looks like that. So let's make a plot. So we have that, and the magnitude square in here that we are going to plot. And when omega is 0, the response is 1, right? So it's pretty easy. At DC, the magnitude response is 1. So any suggestion? How about we check the value when omega equals to the corner frequency? Now we can do that, right? When omega equals to the corner frequency. When omega equals to the corner frequency, suppose that corner frequency is around right here. So when omega equals to the corner frequency, we have 1 plus 1 dividing 1, right? So it's 1/2, right? So magnitude square is going to reach 1/2 when omega equals to the corner frequency. And we know it's monotonically decreasing. So in general, we have something like that. And it goes back to, it approaches 0 asymptotically 渐进的逼近零啊。It approaches zero asymptotically as omega increases. Right? So it's a low-pass filter with a corner frequency right here, regardless of the order n. Okay, it always passes through this point, omega c meeting 1/2. It always passes through, regardless of the order, which is n right here. So our next question is, let's try to evaluate what if n increases. Do we get what will change? Yeah. So it's not that hard to verify either by plotting using computer or just by hand, by looking. So if when n becomes large, I think it's going to, when we increase n, the response is going to be even flatter in the pass band, if you will. This is a stop band, pass band, okay? Pass band. And stop band. So when n increases, we get an even flatter, more flatter, more leveled, more flat pass band, and the transition is going to happen more drastically, more rapidly. Okay, we have a faster transition from pass to stop, while the response at the pass band and the stop band are more leveled, more flattened. Okay, 更平坦化啊. So that's when we increase n. Okay, so with a shallow n, we may have a really shallow response. That's a smaller n. A big n. When n increases, can you imagine? Can you imagine that our response is going to approach more and more to ideal response? So even larger and so on. So with increasing n, we expect this magnitude response to change systematically like that. Okay, increasing n more. Then we are getting closer and closer to ideal response. Okay, with the pass band, magnitude response being 1, stop band, the magnitude response ideally being 0. It's a low pass filter. Okay, so that's the first thing we've successfully, hopefully we have convinced ourselves that this is the way the magnitude response is going to vary when n increases. Okay, so far so good? Yeah? So that's the easy part. The more difficult part, now I think, let me just try to use the entire board. But the next job is a bit more complicated, okay? So we want to show that you're given this system function, or this transfer function, how do we prove that indeed its magnitude response decreases monotonically with a simple form, with a simple expression? That's the tough part, okay? So let's work on that. Question mark, okay? How come? Yeah. So let's check. So first of all, let's draw a picture. Let's make an example, okay? Let's perhaps make an example of a circle on the S-plane, okay, on the S-plane, with imaginary part of S and real part of S. And I'm going to say that this circle has a radius of omega c, the corner frequency. So I said, just pointed out that all the roots of this function, or its poles, if you will, the roots to the denominator, okay, are on this circle, on this very circle. But the angle, if you take a look, the angle, so maybe we can use an example, or maybe not. So let me just say, let's use an example. Let's use an example of, let's say if, for example, if n equals to 5. Yeah, okay. For example, if n equals to 5, then this is going to be a 5th order polynomial having 5 roots. Okay. So if you take a look, this is pi divided by 2, pi over 2, 90 度, 90 degree right here, minus an offset, pi divided by 2n. So if this is, we know this angle is pi divided by 2 minus pi divided by 2 times n. So pi divided by 2 times n, that's what? Pi over 10. So that's 18 degree, corresponding to 18 degree. So let's take a look. So that's going to be 18 degree roughly here, I suppose. Yeah. So that's e to the j 90. Anyway, so that's this term right here. But then we have now a product. So this term, this big term right here is multiplied by e to the j k times pi divided by n. Okay? So e to the j k times pi divided by n. So that's e to the j k times pi divided by 5, with k being what? 1, 2, 3, 4, or 5, right? And we know what is pi divided by 5. Pi divided by 5 is how many degrees? Correspond to 36, right? 36度, okay? So this is 36 degrees. Okay, so we are ready. Now let's plot all the locations of the 5 roots, okay? The 5 roots, the first of it is going to be right here. That's the first root. Located right at how many degrees? You tell me. 108 degrees. That's the first root. And the second root is 36 further, right? 36 further, so that should be in this, around here. Okay? And the third one is right here. Third one is right here. And then we have a fourth one. Fourth one, actually complex conjugate. A complex conjugate. So yeah, just carefully drawing, this basically cutting pizza, sort of. Yeah, you cut the pizza into 10 equal slices. Yeah. And then we have located the 5 roots right here. I'm marking them with a cross, each with a cross. Okay, so far so good? Yeah. So you can even give it a name, S1, S2, S3, S4, S5. Okay, complex numbers on the S plane. 5 of them. So that's h of s. So just simply put now h of s is the same constant. Actually, let's say omega c to the 5th power divided by product. Now it's simply s minus sk, okay, where k goes from 1 to 5. Can you agree on that? Sk, S1, 2, 3, 4, 5 are just right here, right there, okay? So we have this expression for the transfer function. Now basically I'm just calling this entire term as k, okay? So basically that's just what I'm just doing is just to replace the entire expression for each root by denote them by S1, S2, S3, S4, and S5. Okay, now, so that's the first step. And the second step, interestingly, let's evaluate h of minus s. Okay, h of minus s. Sure, so h of minus s is still this omega c to the 5th power divided by the product of minus s minus sk, right? Again, k goes from 1 to 5. That's pretty easy. Yeah, that looks easy. But wait, but all the minus sign here, so I propose that let's try to pull the minus sign to the outside of this product. Can we do that? So in this case, what I'm going to do is to keep the top part but I'm going to create minus 1 to the 5th power, and then inside the product. Now the product still going from 1 to 5 becomes S plus SK. Right? Just moving that minus 1 to the outside. Okay? Moving that minus 1 to the outside. And the next step is let's consider the product of HS with H of minus S. Okay? Now, we have omega C to the 10th power on top. The top multiplies, right? Now how about the bottom part? Here, the bottom part is S minus SK, and there, the bottom part is S plus, right? So when we multiply the two of them, we have the minus 1 to the 5th power is still there, but here, let me say, we have a product of K from 1 to 5. And now we have S minus SK, S plus SK, which is still, in the end, this is going to become a 10th order polynomial. In the end, this is going to become a 10th order polynomial. And where are its 10 roots? The 10 roots are located at S1, S2, S3, S4, and S5, and 5 additional roots at minus S1, minus F2, minus S3, minus S4, and minus S5, 10 roots. Okay? So we're saying that now this expression has minus S1, minus S2,画得不太好啊，不认知啊。You know what I mean? Minus 2, minus S3, minus F5, 4, I mean, and minus S5 right here. Now, when we take the product of these two functions, the entire thing is also a fractional expression, and the denominator has 10 roots. Okay? The denominator has 10 roots. Therefore, can anybody tell me what is that polynomial? When a polynomial has 10 roots like that, which polynomial is that? Can you write down that polynomial? Which polynomial has 10 roots like that? Actually, all these crosses now with 2 different colors, okay? But all 10 of them are roots to one very simple polynomial. That is basically, we're talking about omega C times the 10th root of 1. E 的10次方根了. It relates to E 的10次方根, the 10th root to 1. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are all related to the 10th roots of 1. Can we agree on that? 它是 E 的10次方根啊. So let's write it down. So now, be careful, we have omega C 10 power on top. And let's copy minus 1 to the 5th power. And here, I suppose that we are really looking at S minus omega C to the 10th power. That's a very simple expression. By adding by adding all the 5 extra poles, we actually simplify the expression. Okay, so when we consider the product of HS with H of minus S, the expression is actually simpler. Yeah. It's actually simpler. Yeah. So now, finally, we can now evaluate this expression. Let's evaluate this expression. Now, evaluate. Let's say this is expression A. Okay, this is expression A. Let's evaluate expression A at S equals to J omega and see what we get. Okay, so that's the next step. We're going to evaluate this expression at J omega minus J omega. Yeah. Then now it equals to, I'm just going to copy this right here with minus 1 to the 5th power and J omega to the 10th power divided by omega c to the 10th power. Okay? And so we are really close. Let's just try to introduce some cleaning up. How about we divide the top and bottom by omega c to the 10th power, okay? So that becomes that. And here we have omega c to the 10th power, right? So on top, we have omega, no, on top now we have 1. At the bottom, what do we have? At the bottom, we have minus 1 to the 5th power and minus 1 plus j. I'm sorry, this actually j omega is right, like that, okay? Now, j to the 10th power and omega divided by omega c to the 10th power. So that's what we have at the bottom. So what do you have? What is j to the 10th power? J squared is minus 1, so j to the 10th power is minus 1. Right? So j squared, this is minus 1. This is minus 1. And outside we have minus 1. So minus 1 times minus 1. Then we end up with a very nice expression with 1 on top, right here. That's 1. At the bottom, we have minus 1, so it becomes positive. We have now 1 plus. That's the result that we are looking at, omega c. That's the result that which we need. Okay? That's the result we need. That's the result we need. That's this result. Okay? Which is this result? Can we agree on that? Okay. Do you see that this is our result? The only missing thing, though, is here. We are evaluating expression A at S equal to J omega. But here, this expression J omega H minus J omega. What is H? H is before we add 5 more roots, okay? That's H. So it turns out that this H has real coefficients. We have a polynomial here, and the coefficients are actually all real because its roots are complex conjugates. complex conjugate right here, another pair of conjugate roots right here, and then this is a real root. So h of s, the bottom part, the denominator part of h of s is actually a real valued polynomial. 实系数的多项式 is a real valued polynomial. So therefore, h, note that in general, h evaluated at the minus j omega is going to be equal to h evaluated at plus j omega and conjugate. Now, we have this property right here. Maybe I should put a conjugate sign right here. Conjugate. 复数, 共轭复数, conjugate. So therefore, when we multiply the two of them, they are actually hj omega conjugate, and that's actually the magnitude square for sure. So that finishes our checking. Okay, that finishes our checking. So that finishes our checking. For the case of n equals to 5, okay? For the special case of n equals to 5. Okay, for the special case of n equals to 5. Yeah, so maybe I should take a break to receive questions. Does everything look correct? Does everything look correct? Okay, yeah. And that's exactly the expression we were drawing down here, right? Here, that's 1 plus omega divided by corner frequency, entire thing to the 2n power. Okay, yeah. A monotonically, beautifully decreasing low-pass filter response is what we get. Then, of course, exercise, now you can generalize. So I'll leave it as an exercise to generalize to any given any n, in, let me say natural number, right? Any order. All right, so that's what kind of more tedious part of this exercise. Okay, we have shown that there exists such kind of an analog system, analog transfer function defined over the Laplace variable S. And then we checked, when we evaluate the transfer function on the imaginary axis and take the magnitude square, it has a very nice expression. It has a very clear low-pass behavior. Okay, it is a low-pass filter, a low-pass analog filter. So now, what's next? The next is we need to make it digital. This is not digital, this is analog system. Okay, so we need to somehow use the bilinear transformation, which will turn an analog transfer function into a discrete time transfer function as a function of z. So we're going to go from S domain to Z domain. So how do we do that? Okay, so in the next slide, I'm going to, I think we can erase this. Yeah. We can erase this, and we can erase a few more things. Can I erase this? Yeah, all right, can I erase this? Okay, so next, we are going to study how to go from S to Z, or from Z to S. So it turns out that I'm going to suggest a transformation of S as a function of Z. Okay, let's define this S as a function of Z. Basically, it has this expression of 1 minus Z inverse divided by 1 plus Z inverse. And with a factor turns out to be like that, okay? With a scaling factor. And this is the definition of bilinear transformation. Where there's some TD, let's not worry about it for now. It's a factor that can be adjusted, okay? A factor that can be tuned. And what else? So now, this is a transformation that goes from Z to S, okay? And of course, you can also write the inverse transformation, okay? There's an inverse transformation that can go from Z to S, okay? From S back to Z, yeah. So basically, we're going to see that this is a mapping between the S domain and Z domain. Both are complex numbers. Okay? Both Z and S are complex, right? Z plane. So it's a mapping from S to Z or from Z to S. Turns out that it's actually a one-to-one mapping. Okay, so I think but let me finish talking. I'm on page 6 for the handout. Okay, so we are now on page 6 of the handout. Now, so given this transformation, and we claim that we can design, for any given analog prototype, with a known expression of H of S, 如果 H of S 知道的话, with a known expression for any analog prototype, now our design job is pretty simple. We suggest, my suggestion is that let's define a G of Z as H of S of Z. And period. That's a design. Surprisingly simple. Okay? By using this transformation, we are going to plug in, wherever we see S, plug in this expression. Okay? Wherever we see S, S repeatedly shows up right here, right? Wherever we see S, we will just replace S with this function of Z. And then the result of H of S of Z becomes a function of Z, right? So I claim to you, 我宣称, I claim to you. So surprisingly, this is a design. Okay, this function now is a function of Z, and it defines a discrete time system, which is also low pass. Okay, we begin with an analog prototype, then we end up with a digital design, which is also a low pass filter. Okay, so that's the idea. That's the idea. So that gives us a few further questions. Now, first of all, we need to understand why. Why can we say that this is really a design? What's the spirit? What's the kind of a key concept? Begin with an analog prototype, and now we end up with this discrete time system. And why can we also call that system a low-pass filter? There's a reason, okay? And that has something to do with the property of bilinear transformation. Let's study that. So that's like the why level, but how level, 怎么做? 一个是为什么，一个怎么做, right? So at the how level, I want to demonstrate. Okay, I want to demonstrate. So let's begin. So let's answer the how question first. Okay. Now H of S of Z. What do I really mean? Am I serious about whenever we see S replacing that with bilinear transformation? And yeah, I'm serious. Okay. Let's make an example. Suppose now we have an example of what? I'm hoping that I know how, yeah. Let's Actually, let's use this example, right? On the handout, I'm going to give an example of n equals to 1, okay? But now since now we have this plot of n equal the fifth order, okay? So let's just try to really see whenever we see s, replace it with that, okay? Now let's do that. Technically, that's at the how level. 在如何做这件事情，我们来探讨一下。So let's study how. So now, yeah, we can erase all of these. We don't need them for now. But let's keep this plot, okay? Yeah. Maybe we can take a break, okay? 因为大概10分了啊。So we'll take a break and let's try to figure out that. Yeah.